Model Predictive Control Toolbox provides MATLAB functions, graphical user interface, and Simulink blocks for designing and simulating model predictive controllers in MATLAB and Simulink. These controllers optimize the performance of multi-input, multi-output systems subject to input and output constraints. In this demonstration, I will show how you can quickly get started with this product. Let's use the Simulink model as an example. It's a model of a plant with 3 inputs, 2 manipulated variables and 1 measured disturbance, and 2 outputs. The model is also nonlinear. Our goal is to design a controller for this plant that will make measured outputs follow reference set points while rejecting disturbance and keeping manipulated variables within prescribed limits. Using traditional approach such as PID loops would be difficult here because it would be hard to minimize loop coupling. So we will design a model predictive controller instead. We'll start by launching Simulink library browser, and from Model Predictive Control Toolbox library we'll select MPC controller block and add it to our system. We will now connect this block to the rest of our model like that. We will close the loop, and the only other remaining thing to do would be to add reference signals. Instead of doing it here, in the interest of saving time, let me open a model that I pre-created before, which is exactly the same model, but MPC controller block is already connected to the rest of the model, including reference set points. So now we need to design our model predictive controller. To do that, we double-click on this block, and in this window we click on the Design button. The tool asks us to specify the number of manipulated variables, which is 2, and then Simulink Control Design finds an operating point, linearizes our nonlinear model around that operating point, and when it's done, it brings up this graphical user interface called Control and Estimation Tools Manager, shows us linearized plant, and also creates this node called MPC task. This is where we design and simulate our model predictive controller. We see the structure of our system here, our plant with 3 inputs, 2 manipulated variables and 1 measured disturbance, measured outputs which are fed back to the MPC controller. If we didn't have a Simulink model of our plant, but had input-output test data, we could use this data with System Identification Toolbox to estimate plant model and bring it in using this Import Plant button. We can also specify signal properties here. For example, for our input signals, we can specify if they are manipulated variables, measured disturbances, or unmeasured disturbances. We can also specify signal names, provide signal descriptions, and specify signal units. We can do that for both input and output signals. Once we are done, we can go to Controllers tab and start designing a new model predictive controller. If we had designed a controller previously, we could bring it in using this Import button. In this case, we will design a new controller. It's called MPC1, and the first thing that we need to do is specify the linear plant model that this controller will use for prediction. In our case, we only have one linear plant model, and that's what we will use. Then we need to specify horizons. Control interval is the sampling time of our controller and is going to be 0.2 seconds. Prediction horizon needs to be long enough to capture the major dynamics of the plant. You can set it at the value approximately equal to the settling time of the plant. In this case, it's 10 intervals or 2 seconds. Control horizon will be left at the value of 2 control intervals. Next, we go to the Constraints tab, and here we can specify minimum, maximum, maximum down rate, and maximum up rate for our manipulated variables. So let's do that. Our mass flow can change from -3 to 3. Our second manipulated variable can change from -2 to 2. And we can also limit the rate of change for manipulated variables. If we had output constraints, we could enter them here. In this example, we do not have any. Constraints can be hard, which means that they cannot be violated at any time, or they could be softened, which means that sometimes they can get violated if there is no feasible controller implementation that guarantees absolute constraints. You can soften the constraints by using this button. Next, we go to Weight Tuning tab. This tab is important because this is where you tune the performance of the controller by either using this overall slider or specifying weights for input signals, their rates, or the output signals. In this case, we will leave all these weights at their default values for now. And now we're ready to test our Model Predictive Controller against a linear plant model. So we go to Scenarios, and in the first scenario, we can specify the controller we want to test. We only have one. Against the linear plant, we only have one. And specify set point signals. So in this case, we'll use 2 step changes for step points, with steps happening at 0 and 2 seconds. We will also define a measured disturbance with a step change at 5 seconds. Next, we press Simulate button to check our Model Predictive Controller. We get these 2 plots, and the first one shows the reference set points in gray and the actual response of the closed loop system in blue. We can see that our controller is doing a good job in following set points and rejecting disturbance at 5 seconds. We can also look at our manipulated variables and see that they are within prescribed constraints. We can iterate on the controller design by going back to the Weight Tuning tab and changing weights, for example, like this. We can then go back to the Scenario tab and rerun the simulation. Once we are happy with the performance of the controller against a linear plant model, we can test it against a nonlinear Simulink model. To do that, we need to export the controller to MATLAB workspace. We need to do that because Simulink block MPC controller expects an MPC object in MATLAB workspace. So let's export an object called MPC1 to MATLAB workspace. In the menu for MPC controller block, we see that we need to specify the name of MPC controller. If we now go to MATLAB, we will see that in MATLAB workspace we have the object MPC1. If you look at it, we will see that it has all the properties that we defined in the graphical user interface. And Model Predictive Control Toolbox in general gives you the functions so that you can do everything that you do in the graphical user interface from MATLAB command line. So now we can test our controller against a nonlinear Simulink model by running the simulation, observing the performance of our controller. It still looks pretty good. Checking that our manipulated variables are still within prescribed limits, and if we are happy with performance of the controller, we might be interested in doing rapid prototyping to test its performance in real-time environment or to actually implement the controller. We can do that by either generating C code with Real-Time Workshop or using OPC Toolbox. This concludes the demo.